So we start with chapter number 6, instruction set architecture. Okay, so basically for this chapter they have 6 sub-chapter outline: memory location, instruction architecture, racing mode, assembly language, stack, and exercise. But maybe I just concentrate on number 2 and number 2, 3, and 4. Stack and exercise, and also memory location is just many of the slide I will skip. Okay, majority that's involved in what I call in project is number 2, 3, and 4 only. Okay, so for memory location, I try to make it simple and quick. So we can finish at 10 for both chapter number 6 and number 7. The second phase we will discuss about your project lah, model sim and also purpose. Okay, basic concept for memory. We
tak nampak slide.
Oh, tak nampak slide. Okay, kejap saya share. Kalau tak nampak slide, beritahu ya. Okay, saya share balik. Saya stop. Slide ni nampak?
Nampak.
Nampak? Ni Ini chapter
Nampak,
6
Dah.
memory location. Okay. Tadi dia kenapa hang ke apa macam ni? Konten ni tak ada?
Saya terkeluar tadi, doktor.
Tak nampak. Okay, tak apa. So basic concept for memory basic concept they have if you notice here they have n bits. So it can be 8-bit, 60-bit, 32-bit, and the organization's address 1, 2, 3 until address n-1. Okay, for first word, second word, and until the last word. Okay, this is how the management of memory, and we already discussed in memory chapter last time. Okay. Basically, for this one, they have a k-bit address memory with 2k memory location. Start from 0 to power of k minus 1. So this is called as a memory space. So for example, 32-bit address memory, 2 power of 32, you can get 4 gigabyte total addresses. Okay. This is how the memory address be assigned. Okay, they call it successive addresses, refer as successive byte location. Okay, so how they manage? Okay, you can, if you notice here, how they manage. For example, address 0. Address 0, basically this here. Then address 1, 2, 3. So start with address 4. Okay, address 4. This is 4, 5, 6, 7. Then start 8. ADD 8. So this is for 32-bit address lah. Okay, so they have also what they call as a big endian and little endian. So, but it's not so significant. I just skip. Okay, word alignment. Okay, if you notice, for 16-bit words, word addresses start from 0 to 4. Okay, for this one, 32-bit words, 0, 4, 8. So this is same like the previous slide here. Okay, this is for 32-bit. Okay, so you see here how they manage address 0, 1, 2, 3. So the next line is 4. So 0, 4. So this is example for 32 bits. So 0, 4, 8. Then 12. Not 12. B. Okay. Then instruction. So this is instruction architecture and instruction sequencing. It's about ISA. Okay, ISA. What is ISA? Basically, ISA a set of instruction to be executed in processor. This is in binary representation. If you notice, basically ISA is like an interface between compiler and also processor. So if you notice here, instruction set architecture is right here. Okay, instruction set architecture is right here. Then the application operating system OS compiler is at the top lah. For this part is for the hardware. Circuit design, digital design. So that's why we use quarters in order to to perform those what I call as a digital design. What I call at the skill level, for the skill level. Okay, this is example for ISA, instruction set architecture. Okay, so if you notice, they have different between for Intel and also IBM. Okay, so for Intel, i086 instruction set architecture, they use this is example ADC, add with carry, call, CLD, clear direction, flex, and many more. And this is for IBM PowerPC ISA, ADD, ADDC, ADDE, and many others. So so it's depend on what hardware that you use. Okay, ISA usage. So basically, it's about processor functionality. Okay, so it's tell you about what expression is support, what storage mechanism, and also how programmer and compiler used to communicate from program to the processor. Okay, so this is example. Okay, so we already discussed in chapter 1, 2, 3, and 4 as well. Okay, so operation to perform is addition operation. Location of operand R1 and R3. Location to result. This is for resultant. You store at R0. Then location for next instruction. For example, if they have branch, so they go to branch for the next instruction. So operation types, they have many. Arithmetic, logic, data transfer. For arithmetic, for example, add, subtraction, multiplication, division, logical, shift left, shift right, and operation, operation, data transfer, load, move, store. So this is all under data transfer. Okay, for instruction lesson can be represented into two. RTN, register transfer notation, and the other one is assembly language notation. ALN is called as assembly as well. For RTN, They use basically is for identify the location by symbolic name. For example, location R0, R1, R2. So content of location denote by square bracket like this one, location. So so you go to location, you see what content in location, then that content you transfer to R1. Represent the machine instruction. So in this case, move from location to R1. So all data from the location to transfer to move to R1. The same goes to the addition operation. R2 and R1 then you store as R3. They have instruction format. They call as instruction format based on the number location of operand. They have 3 address instruction, 3 address, 2 address instruction, 1 address instruction, and also 0 address instruction. For 3 address instruction, you can see they have 3 registers involved. For example, for this one, add R1, R2, R3. So R2, R3, after addition, you store as R1. And this is for the 3 address instruction. For 2 address instruction, this one R1, R2, and then you store at R1. For address, 1 address is involved with ACC. ACC is accumulator. So M. So basically, this one is memory address register. So memory address register, you do addition operation with accumulator, then you store at AC, accumulator. The other one is 0 address. So for 0 address is involved with what I call as DOS. DOS is top of stack. Later on, I show you what is DOS. Okay, this is the 3 address instruction. If you notice, they have 3 register involved: operation 1, operation 2, and result. So operation 1, operation 2, then you store at result. So this is the example for the 3 address instructions. If you notice for the instruction format here, they have operand 2, operand 1, and later on all the resultant is stored at the result address. For 2 address instructions, they have only 2 register, operand 1, operand 2. So that's mean operand 1, operand 2, then you store at operand 2. And so this is for the addition operations. If you notice for this one is an instruction format, and they have operand 1, operand 2, then so this is operand that's involved, and then this is operation that you want to perform. Okay, for 1 address, for 1 address, it's involved with ACC is accumulator. So that's mean only 1 register involved. Press operand 1, then you add with the value at the accumulator. Later on, the new value from the accumulator you keep at the accumulator. So the new what I call operation at operand 1 again start or do any other operation for arithmetic operation and those other things. So they what I call keep updating the value into the accumulator, then the new value of the accumulator will be changed. Okay, for 0 address instructions, if you notice here, they also have operand address, but they have this called as a stack. This is if you heard about stack, TOS, SOS. So it's about zero address instruction. If you heard about accommodator, so automatically it is about one address instruction. Okay, the toss top of stack. Source is second of stack. So this is the stack that I mentioned. Okay, so what's happened? So from the operation one, you put at the top of stack. Then this do what I call addition operation. Top of stack plus second of stack. So the new value of top of stack is stored at the top of stack. Okay, so this is what I call to show for the zero address instruction. Okay, this is example for three address format. Addition R1 R1 AB. So for three address format to do evaluation for A plus B, multiplied with C plus D. So what you have to do is these two AB, then you store at R1, CD store at R2, then you do the multiplication between R1 and R2. Later you store at X, the multiplication resultant. For two address, if you notice, this just involved with three instruction: add, multiplication. If you notice, if you do compare between three address instruction with two address instruction, so it involves six instructions. So for two address format, so you need to store A to R1, B to R, then addition. Then addition with B to R1, because at R1 now they have a value A. Then after addition with what I call value from B to R1, so the addition operation, so the new what I call value at R1 after addition operations will be stored here. The other one you involve with R2. So C to R2, then addition D to R2. So R2 and R1 and R2, they have new value. So you do the multiplication R1, R2. Then you move from R1, and because the last resultant is stored at R1. Then R1 you store to X. So you move to X. So it's involved with six instructions. Move, add, multiply, and move for store operations. Okay, for one address format, it's involved with accumulator. And what you have to do is, if you notice, they have 7 instructions. You need to load the accumulator first. Then you add B to the accumulator and store accumulator. Then from accumulator you store to the T. This is any parameter, any register. Then C to accumulator. Then add D to the C to the accumulator and store at accumulator. Then multiplication at T. Then store at X. So if you notice, they involve with 7 instructions. So that means the lower address format, the higher instruction that's involved. For zero address, notice 1, 2, 3, 4, they have 8 zero instruction to perform for the zero address format. So first, this is about stack. you have to what I call from value A to top of stack. Then value B to top of stack. You push, because push A, push B, add. Then push C, push D, then add. Then you multiply. At the top of stack, then you get the value at top of stack, then you transfer. If you transfer, they call as a pop. Pop. The rest add and multiply is same lah. This is arithmetic logic, arithmetic operation. They use the same add, multiplication. But if you what I call for zero address, they have a push and pop. This is a push. You want to move. Pop. You want to stop. Okay. They have also risk style, but I don't want to explain more. Just skip that slide. And also they have about condition code, status flag. So for flag, they have NZDC, negative, zero, overflow, and carry. I believe that in my copy, you already know about this flag. Negative, zero, overflow, carry. So this is the example. Condition branch. Condition branch code flags. If you notice, the value for A is 111, 0, 0. B 0, 0, 1, 0, 1, 0, 1. 0, 0, 0, 1, 0, 1, 0, 0. Okay. So to do the what I call subtraction operation, so you need to what I call do complement value for the B. So after this operation, 0, 1, 0, 1, you get 1. 0, 1, 0, 1, 1. 0, 0, 0, 0, 1, 1. 1, 0, 1, 1, 0, 1, 0. 1, 1 plus 1, 1, 1. Then 1, 1, 1, you get 1, 1. So they have carry 1 here. Negative. Okay, yes, the negative at the MSB, negative, and because the value is 1, so it's negative. Is it the overflow? No, because this is not a signed number. 0, is it 0? No, not 0. If all is 0, so Z is equal to 1. Okay, so this is how what I call the operation condition branch instruction. If you want to ask, you just interrupt me. Okay. Okay. Next is about addressing mode. For addressing mode is a method to specify the location of the operand. So if you notice here, operand opcode, they have opcode, operand 1, 2, and result here. So this is the effective address in order to indicate what is the actual address of the operand. After all addresses computation and addressing mode have been performed. So this is for addressing mode. I just this one I think not so important. You go directly to the last part. I will share this slide later on. I think this is very straightforward. Even for micro P also, you have what I call you do the same way for the IC. But I believe the architecture is you use ARM microprocessor, right? For micro P. Addressing mode. This is for general one. Immediate addressing mode for immediate. Example for the register transfer notation. R4. This is example. Example in assembly. Add R4 with a value 3. This is immediate value 3 to R4. So that's mean you do operation with constant number 3 to the plus which register 4 and store at R4. This is called as a decimal mode for the immediate. Okay, for register, okay, I have to check register number 3 and 4. Do operation for both. Later on, you store at R4. Absolute direct. So this is battery address. So that's mean this one is address 1001 plus with what the value. Sorry, you have to check what is the value at the memory 1001. For example, at memory 1001 value is A plus with R4. What is the value at R4? A. So A plus A, then you store at R4. Indirect. So battery address RI and battery address for the location. So that means you need to check the address at R1, then you do operation with R4, then later you store at R4. So this is all the decimal that's involved. This is general one, but for the ARM microprocessor, it's very specific. It's depend on the technology and also what type technology that you use. For example, Intel or PowerPC, ARM microprocessor, Altera technology industry. Okay, assembly language. Okay, this is type of instruction. They have many, almost the same, but the previous slide is about RTN. For this one is assembly. Okay, so they have, like what I mentioned, they have two different RTN and also assembly. So direct address also almost the same lah. Okay, so you can notice here this is the load operation, for example. Okay? So register transfer, almost the same lah. For direct address, it's involved with memory address. Then you transfer to AC. AC is accumulator. Okay. Okay. For arithmetic logic instruction, increment, decrement, add, subtraction, multiply, divide. So you can notice they have many arithmetic logic instruction, and it's based on the technology that you use. Okay, they have many. Even for the branch. Okay, this is an example for the test. This test is for AND gates. 1 0, you get 0, 0 0 0 0 0 0 0 1 0 1 0 0 1 0 0 0 0 0 1 0 0. They have no 1 1. If 1 1, the value become 1. So this is useful for use for the what I call bit correction. Conditional branch instruction, I don't want to go in deep. Also this one, stack also not so important. Okay, that's all for chapter 6. So the rest is just exercise. But since this slide, this chapter number 6 is not covered for your final exam, I go very fast. But at least you have an idea. Okay, so you can refer to this slide. Maybe as your reference for your presentation for your project. Okay. Okay, we go to the next one about blockchain. This is chapter number 7. Okay. Okay. Before that, any question? Sorry? Ada. Okay. Saya stop recording yang untuk first tu. Saya nak record untuk klik yang untuk blockchain lah. Nanti kita rehat sekejap lah.